I'd like to introduce Rachel Bodeker. She was a speaker we heard earlier today.
AC8XY, and she is the PhD student on the GRAPE project and a student here at Case Western Reserve University. So, Rachel, you can take it away and you can introduce our next speaker.
Our next speaker is a Case alum who's now working at the National Institute of Standards and Technology in Colorado. Everyone, please welcome Aidan Montare, KB3 UMD.
Alrighty, let's see. I don't know if I've done one of these microphones before. This is kind of nice. Cool. Well, let's see. Where's a good place to stand? Everybody seem okay here? Cool. So yeah, hi everybody. I'm Aidan. I am a Case alum, so it's really great to be back here. It's interesting. I was like, the last time I was standing on this stage was like a theater class, and it was very different. Yeah, but today I'm going to talk a bit about a family of statistics that is near and dear to our hearts at NIST Time and Frequency, and that's the Allan Deviation and friends. So some of you may have heard of this, some of you may have not, but I'm just going to only very briefly graze the surface, but hopefully give you a starting point for some interesting things to learn about. So most of you, let's see, I'll start, I guess, by talking about, let's reset that timer. I will start by talking about sort of the classic standard deviation that you all are familiar with, then talk about when that doesn't work, one solution that is popular in my community, some other related deviations, how you use it, and then we'll sort of wrap up. So yeah, let's get started. So most of us have probably seen figures like this in, you search standard deviation and you see something like that everywhere. You've seen figures like this, you know how to calculate it. Okay, that's great, like standard deviation, it's great if you want to describe data with noise, right? And most of you, if you were paying attention in stats class, you might remember that like a lot of the conclusions about this came with some sort of disclaimer that was something like, assuming the population is Gaussian distributed. Okay, so that assumes that our data is independent, and that all the future points are independent, and that even though they are independent, that the history of the data is the best predictor of the new value. And so like that's all great and all, but what happens if my data isn't Gaussian? So what happens if my data looks something like this? That's not too different, right? It doesn't look all that strange. So okay, I can charge right ahead and say, well, I'm going to find a standard deviation anyway. And so I can do that, but this is a little misleading. And to see why, let's make a longer data set out of the same underlying process. And then let's take a look at the standard deviation, but as a function of how much of that data we use to make the standard deviation. So taking longer and longer sections. And so here at the beginning, we're using sort of the first part, then we're using a bit more, and so on. And maybe now you can start to see some of the problem. This is actually kind of a subtle example. But to make that even easier to see, here's our nice Gaussian noise again. And so the difference with this data in green is that the standard deviation doesn't actually converge here. You can see it's narrowing in on some value, but it's still wandering around. Yeah, and so this is actually a type of noise process where standard deviation doesn't converge, like I said. And so it's kind of misleading to just slap a standard deviation on and say, this is my measurement plus or minus so-and-so, because you could just take more data and get a different answer. So yeah, let's see. So I come from now the time and frequency community. I guess originally the amateur radio community. But we've all seen a signal model of some sinusoidal signal, and what we're primarily interested in my community is usually this phi term, and that's the noise in the phase. And so it turns out that it is useful to write a power spectral density of phi. So I have here a couple different kinds of noise. Green is similar to the one we were showing in green before. And you can represent these as different power laws where they go as Fourier frequency to some exponent, and here they are sort of color-coded. And so these kinds of noise appear in a lot of different physical systems. And so it is actually helpful to think about these concretely and have a statistic that can deal with these other kinds of noise that aren't Gaussian. In power spectral density, derivative becomes 2 powers of f, so we can sort of tilt this whole plot, and we were looking at phase. Now on the left, we're looking at frequency. We can think about the same thing. So this is this is the sort of power spectral density of the sort of frequency deviations, and then this is your phase deviations. You may have heard of some of these as like noise colors. So like if you've heard of like pink noise or brown noise, we don't actually use those terms a whole lot in time and frequency, but you've probably heard of them. It's worth noting that here in phase, this flat part in blue represents Gaussian statistics, and then yellow over there in frequency represents Gaussian statistics. So anything towards the right of these plots is less divergent, is what we might call it, and then on the left of the plot is these more divergent noise types, and those are the ones where something like standard deviation isn't helpful. And if you're curious, the one I showed in the example was 1 over f, or flicker noise. And so this is a nice model of different kinds of noise that might be present in our system. Sorry, the thing is kind of hiding what I was trying to read. The question then becomes, great, we can model these things. How do we make sense of data that have these noise processes? Title of the talk, you might have guessed, one tool is the Allan variance. It was first proposed by Dave Allan in the 60s at NIST. These two individuals were key in getting this whole thing sort of started, and it was proposed as a tool to characterize clocks and oscillators. So the core idea is that while the standard variance or standard deviation, you take differences from each value to a mean, when that's not stationary, that diverges. With the Allan variance, you're only looking at adjacent windows in data. And so if this is a function of your sort of window size, and so you can always look small enough or narrow enough into your data that you have statistics that converge in some sense. So here's a figure from one of the original papers that describes this concept. You've got your data, and you're looking at the difference in sort of slopes across these windows that are functions of averaging interval tau, or your sort of window size. And here's the formula, and the key thing to point, do I actually have a little presenter? I think I do. We're looking at the center part here, and we're taking these difference between these adjacent windows. We're not talking about a mean or something over the whole thing. So that's really great. This is kind of a funky construction. Why do we do this? Here's, like the standard deviation, the Allan variance is the Allan deviation squared. So here's some data. This is white Gaussian noise. And with that noise, the Allan deviation reproduces, you can see it sort of starts over there reproducing the standard deviation, so it's normalized it lines up with your existing statistics, and actually reproduces the statistic standard deviation of the mean that some of you might be familiar with, that goes like standard deviation over n. So that's all great, but if it just reproduced something, why would we do it? The interesting part is what happens if we have data that has noise that looks like this. So some mixture of noise types. So this is white Gaussian noise plus some of that flicker noise. And this is really interesting because Allan deviation translates noise types into slopes on our graph. So we can tell kind of 3 main points about this. We can tell sort of on the left side of this Allan deviation plot, which again is a function of averaging interval down on the bottom. We can say, okay, in short short term, the noise here is Gaussian-like. We can look at the long-term behavior on the right side and say that, okay, it's this flicker behavior, and you can go find a chart that tells you what slope corresponds to what noise type. And you can actually use this to say, let's see, can I point with the pointer? Like right here, when this starts to transition, over what point do you want to average your data? So if you're collecting data, white Gaussian statistics, you can average through and improve your measurement by taking more samples and averaging them. Once your statistics are no longer Gaussian, you are either no longer gaining or actually getting a worse measurement by continuing to average. And so this tells you that. Yeah, and it actually tells you something about the predictability of whatever the signal is. So that leads us to sort of our first application of the Allan deviation. This is why the Allan deviation was created, and that is to compare clocks and oscillators to each other. I see some nods in the audience, so this is exciting. So this is sort of a summary plot of, in high level, a bunch of different kinds of clocks and oscillators. And what's really cool about this is, besides being what this was made for, we can compare things that are, many different orders of magnitude of accuracy on the same graph. And these are all based on wildly different technologies, but we can put them into a combined metric. And so something about interpreting this, like some of you may know, like let's look at like a cesium being clock here in yellow. And so the fact that this has a downward slope for a very long time on this graph tells us that you have to average for a long time in order to get the best estimate of frequency. And then sort of on the opposite end of these examples, you look at like quartz, because the graph turns around rather soon, like you need to measure a quartz relatively quickly every minute or so, otherwise you're getting a worse measurement, and you're probably familiar with this, of the idea of the clock walking off. Yeah, let's see. So here's let's talk about some different applications. This one's kind of fun. This is the Earth's rotation rate. So, a day is roughly 24 hours. And this is representing sort of the like variation in that rate. We can make an Allan deviation. This is actually a slightly modified version, but the plot reads kind of the same. And you can identify some pretty interesting things. We can see like periodic changes over the year. We can, say what kind of noise is in this data. We can even use this plot to tell us how often you might need to announce leap seconds. So I'll give you a moment to think about that one. But you can actually like read this off the plot. So hopefully I've emphasized, but the Allan deviation is telling you about frequency instability. And so if this is about frequency instability, then a rough estimate of time uncertainty is something like tau times the Allan deviation. So we can like read off here, and I happen to know that like 10 to the 8th is like 3 years, and if you read this off, it's like, I actually wrote this out so I wouldn't mess it up, but it's like 4 times 10 to the negative 9th, and so that works out to like 4.4 seconds of time uncertainty, is a very rough back of the envelope kind of calculation. And so 0.4 seconds, like you're starting to get to the point you need to announce a leap second. And that kind of works out with what we know about leap seconds. So we can actually make this plot, like why don't we just go ahead and make a plot of tau sigma tau. And so this is even easier probably to see when this starts approaching an order of a second. And so now we have something that's really interesting. Whereas before we were looking at frequency instability, now we're talking about phase instability, or I guess the other way of putting it is the predictability of the phase. So it turns out there's a statistic called the time deviation that does sort of a version of this with a couple extra steps and assumptions. And the reason why I want to talk about it is that it's really good at judging time transfer links. So not clocks and oscillators, but how you get the time from one clock to another clock. And so that lets us talk about our next example. And here's the corresponding plots again. And yeah, so this is something I've been working on. This is NIST Time Measurement Analysis Service. It's a subscription calibration service. It's a turnkey system for people who have like high accuracy timing requirements. You get a box, you get a GPS antenna and cables and all that kind of stuff from NIST. And it gives the measurements of their clock relative to NIST by observing things like GPS satellites. So this is something I've been working on. We are working on upgrading the service. The goal was to evaluate, or one of the goals was along the way, I wanted to say how much improvement are we getting with the dual frequency GPS receiver. So we built some prototype systems. We placed them at our NIST radio stations that you all know and love, and we tested them. And so we can make some TDEV plots, and those really clearly illustrate over what averaging intervals we have improved time transfer noise. And so here's some data from that. So on the left is just a time series of data over, I want to say like 18 days, but I could be wrong. And so in blue, you can see the much noisier data is an old system with a single frequency receiver. It's like 10 years old, so it's also newer hardware. And then we've got two newer systems. And then on the right, we can see this TDEV plot, which tells us again about the sort of phase unpredictability. And you can see that, in the long term, they are measuring the same clock at both ends. So eventually you'd hope that the measurement systems sort of agree on the same answer in average. But at time intervals less than 2 or 3 days, the newer systems have much lower TDEV, and so you can attribute that reduced noise not to the clocks on either end, but to the time link between them. And so this gives us an idea of how much we've been able to improve the service. So at this point, we've kind of blazed through sort of an introduction to the sort of standard or classic Allan deviation. There's a whole family tree of these kinds of statistics. There are, I'm pretty sure, more than even I've listed here. And most of them are developed to address some kind of limitation or challenge that you run into using the Allan deviation. And so I'd be happy to introduce anybody who's interested into some of this whole other family. But yeah, we've just sort of gotten started and seen the basic idea that sort of started this all off. So I would be a little remiss if I didn't mention some weaknesses. I'm going to make this quick because I don't know how much time I have. How are we doing? Okay. So first, non-statistical processes. This is meant to identify, these kinds of power law noises. If you have data that looks like this, please plot it. Of course, you won't know that before you plot it. So that's why you make plots of your time series first. This will probably come as a natural to this crowd, but it's surprising sometimes, like, you get used to something and you're like, yes, I'm going to go plot my Allan deviation, and you kind of forget to actually look at the data. And then you realize you have these weird steps, and this plot, this gives you this weird, half slope, and this is actually complete nonsense. This is just white Gaussian noise, but because of those steps, you get completely misleading results. So always plot your time series. Second, you've got to have uniformly sampled data. There is some work on dealing with things like interruptions to measurement. Important thing is that you can't directly say anything about accuracy with these statistics, because what you're really saying is about stability. And so ADEV, the Allan deviation, and these others are insensitive to a constant phase or frequency offset. So you're not saying, you can't say, this clock is calibrated to whatever. You can only say how stable it is, and you've got to go through some separate process for that. And then error bars are tricky. Insert some kind of XKCD comic here. They're hard. There's a lot of work on it. But ideally, you for these things, you unfortunately need a lot more data than the intervals you actually want to care about. Hey, here's a scary slide, but some of you may have been wondering, what about the frequency domain? And it turns out that like this weird construction I mentioned in the beginning of like, let's take these adjacent intervals and let's subtract them. This is actually just a integral transform. And it's an integral transform specifically that takes the power spectral density of whatever your frequency or phase fluctuations are, combines it with some specifically shaped observation window, and spits out something about predictability of frequency. So it is nothing more than the integral transforms you either love or hate, cooked up into some weird sort of time domain thing, because that's how you actually calculate it, and that's how it was actually created first. Yeah, so that was a sort of whirlwind tour of the Allan Deviation and family. I hope some of you who haven't seen this kind of stuff before will find it kind of interesting. It's useful for saying something about the stability of all kinds of signals, regardless of what they are. And it's one of the things that has led to the fact that time is the most accurate unit we can measure. The ability to identify noises gives you an idea what physical things you might need to do to improve your clock. And so that's led to this tremendous improvement over the decades in clock design. And so it's one part of that sort of history of improvements in timekeeping. And if you take one thing from this presentation, I hope you consider these tools when you want to say something about the stability or types of noise in your data, particularly if you suspect something that isn't Gaussian noise in your time series. Yeah. So thank you so much. Thanks to my boss, Jeff, who provided a lot of this material, and feel free to reach out to me for questions. Thanks.